So, first is Bitfirst search or BFS. Bitfirst search or BFS. Okay. So, this is basically the idea is to, so we have given a graph. Okay. So, idea is to visit all the vertices, we have to explore all the nodes and reachable form. So, we have to start with a vertex, reachable form, given vertex S from V, and we just label this vertex as 0 label. So, it is a label wise. So, we start with the vertex S, like in for the Rubik cube what we have seen in the last class, the Rubik cube, the solve state, this each position or each state is a vertex. So, solve state is a vertex, and from the solve state if we change 190-degree move change. So, that is the one move change, we can go to the solve state like this. So, this is our S, this is the solve state for the Rubik cube, and these are the vertex which is just one step away from this solve state, and these are the vertex which are just 2 steps away from this solve state like this, okay, and like this. So, these are the vertex, final vertex which are basically 11 step away from the solve state. So, this is basically, so we start, so this is basically level 0, level 0 vertex, these are level 1, these are level 2 like this. So, these are level 11, if it is 2 by 2 Rubik cube then the dimension is 11, the length of this is 11, that is the God number. So, this is the level, next level, that means level 1, then level 2 vertex, then this is the level 11 vertex like this. So, this is basically label wise search, and this we want to do it in V plus E times. If V is the dimension of the vertex, V is the number of vertices and E is the number of edge. So, this we want to do in V plus E times, that is the goal. Okay. So, basically we looked all the vertices reachable from S, and we will just look at the adjacency list of each vertex. So, if we start from S, we first look at the adjacency list of all vertices from S which is adjacent to S. So, that will assign as level 1, I mean S is level 0. Then again when we capture all the vertices in level 1, then we go for level 2. So, those are basically adjacent to the vertex which is in level 1. So, those will be in the level 2. So, like this, but we need to careful to avoid the repetition. So, we have to avoid the duplicate. So, a vertex which is already is marked, that should not mark again. So, let us write the code for this. So, the idea is basically level by level search which are reachable from S. Okay, so this is BFS, the input is a graph G, and this is the vertex set, G is basically V comma E, and we have the adjacency list, and we have a starting vertex. So, that is also input of the BFS, we have to start from vertex. Okay, so what we do? We label, so this is the code. We label the vertex S as 0 and the parent of S as null, because that is the starting vertex, and then we assign the I to be 1, I will be indicated as the label, and we assign another set called frontier. We assign frontier which is initially as S, and this we have a loop while frontier is empty, while frontier, that means while frontier is not empty. So, this is basically a Python code. So, next is basically next we put empty and then we take the element from the frontier for u in frontier and we take the all adjacency vertex of u in u, that is v say. We take all the adjacency vertex of, so u is in frontier, this is u is initialized by initial u is s. So, we take all the nodes which are adjacent to u. So, this is the vertex v vertex, and if v is not labeled, then we have to label v. If v is not labeled, so that means v is not marked or not seen. Basically, we have to we have to avoid the duplicate v. If v is not seen, then label of v will be I, okay, and parent of v is u, and we have to append this v in the next, basically next append append this v, okay. We have to append v to the next for the next level vertex. This is 6, 7, 8, 9, 10, 11, say up to 12, and then after this the frontier will be next, and I is equal to I plus plus. I is equal to I plus plus. So, that to indicate for the next level vertices. Okay. So, this is the pseudocode. This is basically Pascal code. This is sorry, Python. This is the Python language. So, this is the code basically. So, what we are doing, we are starting with the vertex s and we are labeling the vertex as 0, and the parent of s is null because that is the starting vertex, and then we are putting this s in frontier, and then while frontier is not empty, we have to do this, okay. And we for each this we are having a set next, and what we are doing, we are taking element from the frontier because frontier is not empty, that is why we are going in this loop. We are taking an element in from frontier, that is u, and we take all the adjacency vertex from vertex with u. So, this is v, and now if v is not labeled, we have to label v by I, okay. And then we put this and parent of v we assign to u because v is the parent of v, and we put this v to the next set, okay. Next set to indicate that is the that these are the next level vertices, and we put next, after completing this we assign this next set to the frontier and we repeat this again, and for the next level will be I plus 1. So, this is the idea. So, let us take an example. So, what is the time complexity for this? Okay, we will come to back to the time complexity. Yeah. So, but what is the time complexity? So, this is we are doing basically what, this is the degree of the vertices. So, this is basically degree of u, and this is basically we are doing while frontier. So, v times, and so this is basically summation of u belongs to v. So, this is again by Hansa-Killlinger order of E, and we are marking all the vertices, that means we are viewing all the vertices, the time will be order of v plus e, because we are visiting all the vertices. So, that is why time will be order of v plus e. Okay. Now, let us take an example of this algorithm. So, suppose you have a graph like this, A, say S, Z, X, D, C, F V, and these are the say edges. This one, say this one, this one. Suppose you have edge from here, this. Okay, suppose this is a graph, this is a input, and you have to run the BFS Bitfirst search on this input. So, it is a label by label search. So, we start with the vertex a vertex S is the source vertex. Okay, so what we do, the frontier is basically S initially. So, that means we label this vertex as 0 level vertex. Okay. Now, we check frontier is empty, no, frontier is not empty. So, we extract so this is the U vertex. Now, we check all the adjacency vertex of this. So, adjacency vertex of this is this 2. So, this is 1 2. Okay. So, this is basically sorry 1. So, this is basically these 2 are adjacency. So, this is the next level. So, now I is 1. So, this is the next level vertices. Okay. So, this is basically frontier I is equal to 0, and so this is the 0 level vertex, and this is the level 1. So, that means frontier of 1 level I is equal to 1 is basically a comma x. Okay. So, now, so this is the 0 level, this is 1 level. So, this is level 0. Now, we have to, now frontier is this, now we have to check all the vertices. So, we take this vertex, if we take this vertex, who are the adjacency list, this is the in adjacency list, but this is already done, this is already labeled. So, we want to avoid the duplicate. So, we are not doing anything on this, this is not labeled. So, we have to going to label this by 2, now I is 2 basically. Now, go to here. So, here we have how many vertices, this is also there, but this is already labeled. So, we are not touching this. So, these are these 2 vertices. So, this is basically level 2, level 2. So, that means basically we have now frontier of level 2 is basically now this set. So, these are this was is next, it convert to the, so Z D C. So, this set. So, this set is basically level 2 vertices, and now this is our next, and this will be in frontier, and I is now I plus 1. So, I is now 3. Now, look at all the vertices from here, these are our U. For this vertex, this is already done. For this vertex, this is not done. So, we have to put this level 3, this is done, this is done, this is already not done, we have to put level 3, and all are for this vertex, this is already labeled, this is labeled. So, all are done. So, now this is basically now the frontier. So, basically frontier 3 is basically F comma P, and this is basically level 4 level 3 vertex. Okay. Now, I is 4, this is level 3 vertices. Now, if we put the arrow for this parent, we have a parent pointer. So, if we put this arrow for this parent pointer, so this parent of this is basically S, because this was captured from S, and then we capture this also. So, parent of this is basically S. So, this arrow is basically parent pointer, and parent of this is basically A. Okay. And parent of this is basically this one, and parent of this is this one. How we are capturing, how we are labeling, so that way. Now, this basically we capture from here. So, we could capture from here, then the arrow should go like this, but we capture from here. So, this is the arrow and this is the arrow. Okay. So, this is the parent pointer. Now, this parent pointer has the importance. So, what is that? Now, parent pointer will give us the shortest path from that node to S. So, if you follow this arrow. So if we start from S, say, so we follow this arrow, this. So this will give the shortest path from that node to this node. So this is the parent pointer advantage. So how to find the shortest path? So basically, if we want to find the shortest path from S to the F to S, so we have to follow this arrow. So basically, the shortest path, finding shortest path, so V, now the parent will reach to parent of V, now again parent of V, so dot and finally we reach to S. Okay. Now this is the shortest path from S to this is the shortest path from S to V this can be proved. Shortest path in the sense here there is no weight, but shortest path is means number of edges we are visiting is less in that sense. Okay. So this is basically called Bitfirst search and its time complexity is V plus E. Now we will talk about depth first search. So this is also another way to explore a graph. So this is called DFS. So in short, it is called DFS. Okay, so DFS has many applications like edge classification and topological sorting. We will see about those. Okay, so so just to so this is basically it is basically the idea is basically this is backtracking. We follow all the paths until we stuck. We start from a vertex, we follow all the path, we just keep on going until we stuck. So this is a nice example of match. So if we just follow, if we stuck, then we will come back to there and we try for other path. Okay. So that is the way. So we will do the backtracking because we may stuck. So we follow the path until we got stuck. So follow path until we stuck. Now once we stuck, then we will backtrack, we will come back to that previous position and then we choose the another path and we continue until we stuck there like this. So we start from here, say we keep on going until we stuck, there is no way to go, then we come back here, then we explore the other path from here, again if we stuck, we will come back, we will explore the other path from here like this. Okay, so backtracking is necessary here. So recursively we will do this. So backtracking we need to do, and this will this is a recursive call. Recursively we explore the graph, because when we again stuck, we will come back there, we will choose the another path there. But we have to be careful that there should not be any repetition, there should not be any duplicate repeat of the vertex. So if a vertex is marked, then it should be done. Okay, so let us just write the pseudocode for this. This is also we will try to write in Python. Okay, so this is basically so parent of, so we just, so it has two code, one is DFS visit, which is basically we have a graph input and we have adjacency list, and here we have a source vertex. So, DFS visit is having a input with source vertex. Okay. So, for this parent of the source vertex is null. So, what we do, we check all the adjacency list of S, okay. And if it is not explored, that means parent, we are using the parent to indicate that whether we have seen this vertex before or not. If it is not seen, so if V not in parent, that means if V is not seen before, then we label this V parent of V as S and we call BFS visit. This is the recursive call on this V. So, graph adjacency list and on this V. So, this is a recursive call, okay. Very simple code. So, this is the recursive call. So, when we just follow that, so we start with S. So, this is S, we start with S, we go to V, then again we call this BFS visit from V if V is not done, and we keep on doing. Once we start, we will come back to here, we will choose another vertex V. So, this is for all the vertex which are adjacent to S. Okay. So, once we explore with this, so that is why it is a recursive call and it is backtracking. Okay. So, this is with the one vertex. Now, the main code is basically BFS visit, BFS, which is taking the graph and the adjacency list. So, here is no starting vertex. So, we just having parent as empty and then we choose a arbitrary vertex as S. For S in V, if S is not in parent, S not in parent, that means S is not explored. Then what we do? We just assign parent of S as null and we call this BFS visit on S. BFS visit on G adjacency vertex and S. Okay. Okay. So, very simple code. So, we just start any arbitrary vertex as S, then we, if S is not marked, we have to choose a vertex which is not marked, then we will explore this. Let us take an example. So, before that, what is the time complexity for this? So, again time complexity will be depending on, this is basically or degree of S basically, and this is doing for all the vertices. So, basically summation of the degree of U belongs to capital V. So, this is basically order of E, and since we are visiting all the vertices, so this is basically the time is basically order of V plus E. Okay, because we have to visit all the vertices. Now, let us take a quick example. So, we want to take a quick example. Suppose we have a vertex A, B, say D, E, we have C vertex over here and say we have a F vertex. Okay. And then suppose we have this edges, this one, this one, this one, this is a directed graph, it can work for undirected graph also, this one and this one, and we have a self edge over here. Suppose this is the given graph and we want to explore the DFS on this. Okay. So, now we have to choose a vertex for starting with. Suppose we choose this as a S. So, this is say we denote by S1. So, this is our starting vertex, say S. So, now we just need to find out. So, now we have to start from S, we need to explore, keep on exploring with all the adjacency vertices of. So, we choose this. Okay. This is the number 1. Then this is, we call again BFS on this. So, this is having adjacency vertex this. So, we go there. So, again this is adjacent with this, we go there. So, this is say 2, this is 3, this is the ordering we will visit the. Okay. Now, we have to call BFS visit from this, but this is having a vertex adjacent to this, which is already in the parent, which is already marked. So, we stop here. Once we stop here, we come back here, we have to see all the adjacency vertex of S. So, that is the backtracking. So, we explore a path, we come back because we stuck here, we come back here, then we see this is the another adjacency vertex of V. So, but this is already in the parent. So, we are not doing anything for this. So, this is the way. So, this is the S1. Now, we choose another vertex from this graph which is not done, that means which is not in the mark at a parent. So, this is basically the vertex. So, we may start with any of these vertex. So, we may start with this S2. Okay. If we start with the S2, then this is our new S. So, this is the vertex, but this is already in, this is already marked, this parent mark is already done. So, this is explored. Now, this is not explored. So, we have to explore this. So, this is basically 3. Okay. So, this is basically not explored. So, this is we have to, so there is no need of this numbering anyway. So, this is no. So, now this we mark the parent of this as this. So, this is also marked as a parent. Now, we call this, but this has only self loop which is already done. So, we stop, there is no other vertex left out. So, this is the BFS search. So, we just start with the vertex and we keep on going until we stuck. Once we stuck, we will come back to that vertex, we explore the other path like this. So, this is the depth first search. Okay. So, now this, so now we can label the basically we can label the edges. So, we can classify the edges. So, this is called edge classification. We can classify the edges. How? Now, this edge basically forms a tree. Okay. So, this edge will be forms a tree. I mean, if it is connected, then it will form a tree, otherwise it will form a forest. So, these edges are called tree edge, which forms the parent basically, tree edge. This edge called tree edge, which basically forms this bold color edge, which basically forms the parent. Okay. And other non-tree edge, like this is a non-tree edge, say this one is a non-tree edge. This is basically called forward edge. Non-tree edge is either forward edge, back edge or cross edge. So, why this is called forward edge? Because we have this ordering of the this. So, this is coming after this. So, this is a edge from this to this ordering. So, that is why it is called forward edge. Because this is the edge we have visited first, and this is the edge after that. So, this is the edge from this ordering is which vertex we have visited first earlier than the which vertex we have visited later on. So, those type of edge is called forward edge, but this edge, if we look at this edge is basically going from this to this. This we have visited later on and this we have visited before this. So, this is called back edge. this is called back edge, and this edge which is connecting the two different tree. So, this is called cross edge. I mean, other than back edge and forward edge, any edge is called cross edge. Okay. So, that is the classification of edge. So, this will help us to have some application like how to find the cycle detection of the edge. So, let us just quickly have that. Okay. So, one application is cycle detection, how to detect a graph is having a cycle or not. Okay. So, given a graph, so this is the theorem. So, if there is a back edge, then there is a cycle. So, given a graph has a cycle implies if we run the DFS, the DFS has a back edge. Okay. This is vice versa. So, if DFS has a back edge, then it has a cycle. Okay. Now, let us prove this, let us try to prove this. Okay. So, first of all we assume that DFS has a back edge. So, we are first proving this side, DFS has a back edge. So, that means what? That means we have this type of things, okay, and this is going these are the tree edge and we have a edge like this. So, this is back edge. So, these are the tree edge, the forming the tree edge and this is the back edge say. So, obviously, if this is a back edge, this is a cycle, okay, because this is a back edge. So, it will form a cycle. So, that is quite clear. So, if the DFS has a back edge, then there is a cycle. So, this way you can detect the cycle. Now, other way, if there is a cycle, then how to show the DFS has a back edge? So, other way around. So, that is also interesting. Suppose a graph has a cycle, G has a cycle. Now, we have to show the DFS has a back edge. Suppose this is a cycle, say we have say V1, V2, V3 like this, V4, V5 dot dot dot, say Vk like this dot dot dot. Suppose there is a cycle. So, it start with V1 and it went to V2. Now, we do not know in our BFS algorithm which vertex we select to start. So, if we select, say for simplicity we can say we are selecting that vertex V1. If we select this vertex V1, then it will keep on going. These are all tree edge like this, these are all tree edge, these are all tree edge like this, these are all tree edge, but this will be back edge because this cannot be tree edge because this is already done. So, in that case this will be the back edge. Okay. So, in that case this will be the back edge. Okay. So, this is one application to find the cycle in a graph. There are other applications also like topological sorting and job scheduling algorithm. So, those are in the textbook. Thank you.